So for question number 11, you need to use some chemical strategy. Just having the knowledge isn't going to be good enough. You need to find out what the planar representation of 1R, 2S, 4S would actually be. So when I was working this earlier, I'd like to just show you how I went about doing it. So all I really did was just guess at a structure. So I drew a cyclohexane. And I'm going to show you what I guessed at. So it's 1, 2, 4. So let's assign R and S. I'm going to start with iodine. Either I'm going to be right or I'm going to be wrong, and if I'm wrong, I'm just going to flip the answer. So iodine certainly is going to have priority 1. Hydrogen will have priority 4. The carbon with the methyl group branch point will be 2, and the methylene will be 3. And as I go from 1 to 2 to 3, notice that I am moving clockwise. This would be R, and I need it to be R. So that is just fine. So what I'm going to do, as I'm putting all this together, is I'm going to have my final compound rendered in purple. Carrie, I'm sure you can tell me what the actual color is. I know it's not frickin' chartreuse, that's for damn sure. But I know this iodine now is correct. Alright, so let's go to carbon 2 and this methyl group coming out, going in, which means hydrogen's coming out. So carbon 1 will be where the iodine is. Carbon 2, the methylene group. Carbon 3, the methyl group. And of course hydrogen is 4. Now hydrogen is not oriented away from the viewer, so we'll need to flip our answer. As we go from 1 to 2 to 3, that is S, but we've got to flip it to R, and we're looking for S. That means rather than going in, the methyl group must be coming out. Finally, let's look at carbon 4. And so I'm going to be a little careful here. These are all going to be CH2s. So you need to look at what they're attached to. This is attached to a CH2. This one is attached to a CH3. This will be priority 3. Priority 4, of course, will be the hydrogen, and again, it's coming out towards us. We need to pick between these two. This one is going to be 1. It's going to win. And of course, this one is going to be 2. I'm going to go from 1 to 2 to 3. That is S, but again, I need to flip it because the hydrogen is not going away from us. So that means this would be R. We want this to be S. Therefore, the ethyl group also must be coming out towards us. And once you have this, you really got the problem right where you want it. So now that I know what my final compound is, we can draw the chair conformation and find out what our lowest energy conformation will be. Of course, we're going to have an equator. And we know we want the biggest, bulkiest substituent to be equatorial, so I'm going to choose this to be position 4. And so this is going to angle up. This would be carbon 3, this will be carbon 2. We have the methyl group also equatorial, angling up. And on 1, it's cis, it also needs to be going up. That means the iodine is axial. So we need both of the carbon groups equatorial and the iodine group axial. That is going to be answer choice C. So for number 11, the credited response is C. We're going to rank compounds in order of increasing boiling point. So we have hexane, we have 2,3-dimethylbutane. Notice that have exactly the same number of carbons. We have butanol, and we have methyl propyl ether. The more significant the IMFs, the highest they're going to be. So this is going to be the highest. This one is going to be the lowest. This will be the next lowest. This will be the next highest. Now when we rank these compounds, we want to rank them in order of increasing boiling points. Therefore, we want to rank them such that, and I'm going to go ahead and label these as A, B, C, and D. D is the lowest boiling point, then A, then B, then C. That is answer choice D. So number 12, the credited response is answer choice D. And let's finish up this slide with number 13, where we have a series of charged intermediates. That's supposed to be a double bond. All right, just about there. First of all, the one that's going to be highest in energy has absolutely no resonance. This is going to be the highest in energy. The one that's going to be the lowest in energy is the one that has the most resonance. That's clearly the third molecule. Now, we have a choice between this molecule and this molecule. There's something special about this enolate, such that when I do the resonance, everything has a 0 charge. So this would be the next lowest, and then this would be the next highest. And we are tasked with ranking these in decreasing stability. We want to rank these in decreasing stability. So the most stable should be ranked first. So the most stable would be C. And then it will be A. And then it will be D. And then it will be B. And this should correspond to answer choice B. So number 14 is an interesting question. We know that when we add Br2 across the double bond, we get anti-addition. So one way we could render the product, of course we could also do the enantiomer, is this way. That doesn't look to be symmetrical, so we're looking for the meso compound. Let's go to the next one. We know the next one isn't because, again, it's anti-addition. And the left half is not the mirror image of the right half. So we can effectively eliminate B from being an answer. OSO4. Gives you syn hydroxy. That doesn't look to be one either. Of course, HBr isn't going to be one because there's no way this is symmetrical. So really, we are left with the possibility of A or the possibility of C. What we want to do is rotate around this bond so that these groups are going in the same direction, and we need to do the same thing here. So if we do this, one of the groups will stay the same, but the other one's going to flip. And for the same reason that this isn't meso, this isn't meso. Look what happens with the dibromo compound, however. This one stays the same, the other one flips, and voila, you've got your meso compound. So the credited response for 14 is answer choice A. All right, number 15. How many stereogenic carbons are there in this first generation birth control pill? So let's draw its structure. Of course, all these birth control pills are derivatives of progesterone, which is a steroid hormone. It is responsible for maintaining the overall health of the uterus during a pregnancy. And essentially what happens is it sends a chemical message to the rest of the body that a person is pregnant, such that the levels of LH and FSH will diminish and the menstrual cycle will begin. So essentially will prevent ovulation by a chemical trick. It was first synthesized 60 years ago at Stanford University. It's a big, big, big deal in organic synthesis. Pretty complicated molecule, and we've got no shortage of chiral centers. So let's mark them. This is clearly one. This is one. This is one. This is one. This is one. And this is one. We have 1, 2, 3, 4, 5, 6 chiral centers. So 15, the credited response is D. 15 is D. Moving on to number 16. Got another stereochemistry question. Remember, there are I think 7 stereochemistry questions on the exam. So this is another big area to emphasize because these problems are not inherently difficult if you do plenty of practice. we want to find the configuration at carbon 3 and at carbon 6. Let's take these one at a time. So when we start comparing these two carbons, well, actually we have 3 carbons. We know clearly this one will be 4. We have a CH2. This one has a CH. This one has a CH. This one's going to be 3. And between these two, you have the double bond's going to win because this carbon's more important than this carbon. So this will be 2. The hydrogen's already rotated away from us. And so this is going to be S. So for 3 needs to be S, so we just want to get rid of A and B. Secondly, fluorine will be 1, hydrogen will be 4. Whoa, 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 whoa. Just saw that, just saw that. Never mind, I was joking. Fluorine's 2, sulfur is 1, this carbon is 3. You would say 1 to 2 to 3 is S, but the hydrogen's coming out, it must be R. So 3S, 6R, that is answer choice C. So for number 16, the best answer is C. All right, moving on to number 17. We want to do the relationship between these two compounds. I did my best to make this as convoluted and confusing because if you can do this one, you can do any stereochemistry problem, period. And there are really no shortcuts to this. You want to find R and S. There maybe is one gimmick that you want to find. I don't know that you necessarily need to do it. You could flip 2 labels twice. For example, why don't we, on the bottom, why don't we flip the Br in the methyl, and then let's flip the OH in the methyl. So we want to flip Br in the methyl, and then OH in the methyl. Notice this bottom equals this bottom. So these are the same configuration. Doesn't matter if they're R, or SS. They're the same. Secondly, why don't we flip the H and the Cl? Let's put the H here. The Cl would go here. And then let's flip the methyl and the Cl. And by golly, what you're going to see is you got the same here as well. Therefore, these must be the same compound. Now that's kind of a gimmick. It works really well and it'll work all the time. You could assign R and S to both and you should get the same answer. Number 18, which is the best SN1 substrate? So it needs to have the most stable carbocation. Okay, so if the leaving groups leave, let's just go ahead and make those leave. There's no resonance stabilization here. Now you could have a rearrangement to get that. This one is allylic, so you've automatically got this. This one would have to rearrange. This one would have to rearrange. B is my best answer. B is the most reactive SN1 substrate. So the answer to number 18 is B. Number 19. Which the following factors does not influence the rate of an SN2 reaction? There is never a carbocation intermediate. So the obvious best answer is C. In an SN2 reaction, you will have sterics. That's why primary substrates are more reactive, and by that I mean they have a lower energy of activation. Quality of the leaving group affects an SN2 reaction and an SN1. And of course, the strength of the nucleophile matters in an SN2 reaction. But C, carbocation stability does not affect an SN2 reaction. Finally, let's finish this particular version of the screencast with number 20. And we have another nomenclature question. Whenever I get a nomenclature question, I always look at the answer choices quickly just to see what they are testing. For example, they all have E, so they're not testing if I know the difference between E and Z. They all have 5-ethyl, octan, 6-ene-3-ol. This is a stereochemistry question, so I just need to find out R and S. And it's important to realize that so you know what to do. Don't do too much of a problem. So OH would be 1, this carbon will be 2, this one will be 3, H is rotated away. This goes clockwise, so it is R. That means I can eliminate C and D. Now when I come over here, 1, 2, 3. Now this hydrogen's coming out towards us, so we're going to have to flip our answer. This looks S, but it's actually R. So the best answer is going to be A. The credited answer for number 20 is A. And I'm going to stop this screencast. We'll pick up with number 21 on version number 3.